All right, good morning. Let's get started. I should connect here. Okay. Holiday break. I hope the weather was okay around here. Let's see. Let's make this bigger. Here we go. That's better. All right. And let's get more organized. So let's start by taking a look at the presentation calendar and work backwards from there. So we're going to have a presentation on Scheme on Thursday. So Scheme's a more modern version of Lisp, one of the early functional languages. And then this is the calendar for the rest of the semester. So next week, again, we're going to have just one presentation, and then we're going to have almost a firework of presentations during the last 2 weeks of classes and then during finals week as well. So the plan, there's going to be, I believe, a quiz, I think, on the 12th. Well, let me double check the important dates here. So we're all on on this very same page. No, okay, so that's actually a proper test. So on April 12th, we're going to have a proper test, and followed by project discussion, and then the presentation on R, the statistical language. And then we're going to continue normally, and then unfortunately, or fortunately, depending on how you look at it, our final exam slot is Saturday, May 5th from 9 to 11. Just to make sure we get that on your radar, yes.
Will test 2 be in class or out of class test?
Oh, it'll be here in class. Yeah, it's so the remaining tests will just be they will be administered here in class and followed by a lecture. So test 2 will be about a 50-minute test, roughly. You know, not quite the entire lecture period, right?
So will it be like the quizzes more so, or will it be like multiple choice with some programming? Or?
Yeah, like more of the latter. So there will be a little bit of programming in it. You know, combination, multiple choice, true, false, some matching maybe if I can figure out how to do that, and then some programming as in most of these tests. So yeah, and then the tests as usual will focus on the more recent materials. So they're not designed to be cumulative, although there will be cases where it's inevitable to rely on some of the earlier material because the material just builds on each other, right? So I will send out a roadmap, but at the latest over the weekend, okay, and then that's our final slot. So the way we're structuring that is we're going to hold this final test for the first, let's say, again, 50 or 55 minutes with a grace period, and then we're going to have the remaining presentations, okay? The project deadlines are designed kind of to line up with this, or actually a little earlier, so you can get those things out of the way. So take a look. Maybe we should take a quick look here together. So the main one you need to keep in mind right now is, of course, 3B, which is due on the 13th. And that's what we're focusing on right now. Then graduate students in particular should be focusing also on 2B, kind of in addition to 3B. So what you could do if, let's say, you're part of a team, if you're a graduate student, you're part of a team with an undergrad, and the undergrad doesn't want to do this for extra credit, you could maybe team up with another grad student who's in the same situation, or you could, let's say, have a discussion with your teammate and make them realize that this is a great opportunity, not only to earn some extra credit, but also to learn some, in my opinion, rather intriguing concepts and techniques. So let's actually look at those materials during this week, right? Because all of the background for Project 3B is in the recorded lectures. Who's had a chance to watch the 2 recorded lectures? Okay. So those who haven't, I very strongly encourage you to watch those because, it's very convenient. You can rewind multiple times. You can really get to the bottom of things. And they cover everything you need to know to succeed in Project 3B in detail. Right, so I guess you've I hope found that to be the case. It's very detailed and walks you through, first of all, it covers the concepts and then walks you through the guiding example and is really intended to set you up for success with everything you need for Project 3B. Okay, so I think this means we're now organized. So any questions, any organizational or other questions right now? So then let's see, are there any questions about Project 3B at this point that you'd like me to address? Hi. So let me just recap, and then it'll make more sense once you watch the 2 lectures, the 2 recorded lectures. But basically, right? So what we're doing in Project 3B is add another stage of the little tool chain we're building here. So this is kind of a back end that we're adding, but it's an interpreter as opposed to a code generator, right? So the interpreter actually just works directly on the abstract syntax tree that your front end will create based on your input source, right? So once you have that abstract syntax tree, you can kind of try to execute that as a program, and that's what the interpreter does, right? So it corresponds to what in the earlier expressions calculator example is called the evaluator, right? Because in the expressions example, let's take a quick look. So if we look here, so this is of course the main, and there is a loop, right, a for each loop, where for each line of input, we process the line and then prompt for the next line. So this is your top level loop. And then what do we do for each line? So each line is an expression that we evaluate, just like something you type on a calculator and then hit enter. or the equal sign on the calculator, and then it evaluates the expression you typed, but it has all of this diagnostic output so that we understand better what's going on. But the key thing that this does, so it parses your input, and then this is the abstract syntax tree. So on line 12, expert, that's your abstract syntax tree after successfully parsing. Then it gives you this feedback, shows you what the parse tree actually looks like. That's the two-formatted string, and then it prints these statistics, just kind of for practicing recursive behaviors on tree structures. And then comes the interesting part, which is it evaluates the expression. That is really the interesting part on line 16, right? So let's take a quick look at that. But that's really what the value that the calculator adds is evaluation. So if we look here, in the case of arithmetic expressions, this is particularly simple, right? It just says, well, whenever we have a node in the abstract syntax tree representing an operator, what do? Well, we evaluate the children. So first of all, what do we evaluate to? Well, we assume that these are integer expressions. So it's a simplified thing. So these are not even floating point numbers. It's a simplified thing, so we're evaluating to integer expressions. So the evaluate behavior, what is its type signature as a function? So what are the domain and codomain? Domain is abstract syntax tree of type expert, right? Because that's the argument type. The codomain, meaning the result type in programming terms, is int, okay? And for every possible branch, we need to look at that variant of our data type, our abstract syntax tree, and produce something of the desired result type. So that's what these behaviors typically look like. So a constant representing number or value C evaluates to that value C. That's the base case. That's the key thing here, right? And then these others just simply for a abstract syntax tree node that represents a minus, you evaluate the children, you're getting two numbers, and then you're actually using the real minus operator to subtract those, right? And that's how it works. So it's very, very simple for arithmetic expressions. For statements, it includes this, but it becomes a little more interesting because this is completely stateless, right? There's no history here, whereas the whole point of bringing in variables and assignment and the ability to then use the variables in these expressions is that the variables give you state, named mutable state. Does that make sense? So that's where we're taking things to the next level in this project 3B, right? So we have to build in the kind of support structure we need to manage the variables, and that's basically a memory store which maps from the variable names to mutable variable values, and that's basically where we're actually storing the variables. And you can, of course, see this in some of the key examples, like under MISC, right? And I think there are links to those things from the project description. So let me just recap that, and then we'll dive into the discussion that we have to be able to make sense of project 2B. So if you look here at MISC Scala imperative, so there happens to be a parser, but let's see. Yeah, so there's a parser here. So this will actually do most of what you need to do for or it guides you in what you need to do in 3B, or 3A, actually, this parser. You've probably seen this. But then there's an execute. So let's first take a look here at the abstract syntax. So it's very similar. So sequence here is similar to our block, right? All of that stuff is here, right? And the execute is the guiding example for for 3B. And what we're doing here, although it's simpler, this is one way of doing it, and another way of doing it is what you see in the simple imperative algebraic. So the algebraic part is related to project 2B, okay? So let's not focus on that one too much, but as part of the discussion of 3B. But if you look at evaluate here, let's see. Okay. So actually, they're both doing it similarly, in the sense that when we look at where we're introducing a variable, let's see. So remember what's going on here. Right, so there's a key difference we need to recognize and consider when doing project 3B as opposed to these examples. Because the language we're doing in 3B is a little different. So this is just so you don't get stuck in a kind of dead end here. Most of the ideas you can use. So what you see here is basically the evaluator, and in the upper half you're seeing the code that evaluates arithmetic expressions, which is like what we had before in the expressions example. Does that make sense? So same idea of if you see a plus node, you need to evaluate the left and the right children, and then use the native plus operator to actually carry out that arithmetic operation, right? But what's all that other stuff and that extra argument for the store? So the store is where whenever there's a variable x or y in the expression, you can find the value currently associated with that variable, because it's not a fixed value that's associated with the variable, because using assignment statements you can change it. So at one point that variable stands for one value, and then you do things that affect the value of that variable by assigning to that variable, and then when you look at that variable later you get the updated value, right? So that's the kind of thing we have to support in this. So that's kind of the essence of making this an imperative language with named mutable state. So the names of the state are the variables, and mutable means that you can actually alter or change over time by assignment what value is currently associated with a variable. So whenever you assign to a variable, then whenever you assign a value to a variable, then that value will be associated with the variable until you change it again, right? It's your familiar behavior of mutable variables. So how do we need to support this? Well, depending on how your language works, okay, and this language is a little different from the nano JavaScript that you're doing in Project 3B. The difference is here, it assumes that all of the variables are declared up front. That's why you can get by with the store as an immutable map, and only the things that the variable names map to are mutable. So what you're seeing there on line 29 is this type definition of a store. So it's a map from the strings representing variable names like X, Y, Z, and so on, to actual containers that can store a value in such a way that you can change that value, right? So why is it called L value? You might have heard this, when looking at C programs, they talk about this kind of stuff. In 264, you would probably have heard about this. So L value and R value, it simply means an L value is something that can be on the left side in an assignment. That's really all it means. So L value, something that you can assign to. R value, something that you can look at, and that can be part of an expression. Okay? So if we look at a variable, so let's say we have an expression like this. So X is 2 times 3 plus Z. Okay. So this is interesting because it shows you that depending on where the variable appears, you could be referring to it or using it in a different way. So let's look at a little picture here. So suppose, here we have an assignment, Z becomes 7. So let's look at our store that we need to support that. So we need, let's say, a map from X to some box, and then a mapping from Y to some storage box. And then initially, there's nothing in there, but then when it says here Z becomes 7, I think we need a Z rather than a Y, so correct that. Z. No. Let's do it again. X and Z. Here. Okay. So when we say Z assigned 7 or Z becomes 7, what happens? Well, we're putting the 7 in here, right? So in this case, we're interested in the L value of 7, meaning that the box we can put a value into. And whatever value there was before, what happens to that value? So let's look at this example. So X becomes 3. Okay. So this means now we're going to put a 3 into the storage box associated with X. Now we're putting a 7 into the storage box associated with Z. So here we're interested in this storage box, which is basically the L value we can stick a value into. What about here? What's going on here? Okay, so we evaluate this, so 3 plus Z. What do we do here? Oh, Z, okay, so that's got to be this variable. Then we look at what this variable maps to in our store. And now what are we interested in here? The box itself or what happens to be currently in the box? What's in the box? So we got this value 7 and put it here instead of the variable, right? So we get the current value of the variable. So that becomes 3 plus 7, 10 times 2. And what do we do? So we have a value 20 here. The evaluator gives us that, right? How do we do that? Well, if we see a variable, it looks up the variable in the store. See, that means Oh, there's an occurrence of a variable, a use of a variable. So we got to look that up in the store. That's where it says store as a map, and we're looking up whatever there is at associated with the key name. So we're just following this mapping. That's what happens there in the case of a variable. Okay. And now we need to look at, for example, if there's a plus. So line 33, there's a plus, and the right argument is a variable, okay? So the right child. So what happens here? Let's go through the steps. So we're saying apply store right, and right is this z, okay? So we're recursively invoking this with the same store and with s being our variable z. So that takes us down to this branch, line 37. And it says, okay, look up z in the store. What does that give us? So far, just a box. The box. But we were here, right? We were here, and there's something else we need to do where it says .get. And that's the part where you say, actually, we got to go inside the box and get the value. So that .get gives us this value 7 and inserts it here. And then that's how we got the R value currently associated with the variable z. Okay, so this gives us a new value. It happens to be 20. And we're assigning that to x. What do we do? Well, we look at assignment. It says the R value is whatever the right child. So the assignment has a left child and a right child. Right? The left child is just the destination of the assignment. So the R value is here. So what this does is basically create a nameless cell with a value 20 in it, right? Because every time you have an arithmetic expression, it creates an empty storage cell or a new anonymous storage cell with the value of that expression stored in it. So we got this 20, and then that's our R value. And then our L value is whatever we have on the left, which is variable x. And that's why when we evaluate variable, in this example, it doesn't do the get, because in that way it could be on the left side. And then we only actually go that extra step to go into the L value to get the R value stored in the L value. We're doing that only when the variable is part of an expression that we're evaluating. That's how this example works. So then we have basically this L value, and it says get the actual numeric value in the R value. So on line 41, it gets the value 20. Okay? It goes into this box and gets the value 20. And the L value is just x. So it's actually whatever x maps to, so it's this. And it says, so L value set to whatever we got here. So this number 20 goes in here. What happens to the number 3 that's currently in x? It just gets thrown away. That's exactly right. That's how variables work. You're already very familiar with variables. And this just simulates what happens, or it implements, you could also say, what happens here. So the set is up here. So set means you're basically assigning a new value to the L value. And the roles are, again, here. let's see. This is the variable x as an L value. And here the variable shows up as an R value. So that's really all there is to these definitions. It's important to get those straight. Okay. So now how is 3b different? So in 3b, I suggested a simplification that in assignments, we always have just a variable on the left, whereas here, if you look at assignment here, this is a little more general, because this is a language that looks a little bit more like C. And in C, you can have actual more general expressions on the left. So that might be a difference between your abstract syntax tree and this one. So then you can simplify accordingly. But really the key insight is that your interpreter, meaning what's called the execute here, should basically have some kind of store where it looks up the variables and where it updates variable values also. So that's really the key addition that we need to support the presence of variables in our project 3b as opposed to the expressions examples. And if you look at the language here, so there are some tests. That's the thing I wanted to re-emphasize. Okay, well, there aren't separate tests here, but let's see. There's some stuff here. So the key difference is that in this example, we have to predefine a store with the variables we're going to use in the program. So we have to declare the variables up front. So it's a little bit like static allocation, like in Fortran, right? You remember Nick's talk on Fortran, right? Where in older versions of Fortran, variables would have to be pre-allocated statically and therefore declared up front. So it's very similar. And then we could write a little program, and this program corresponds to, as you can see here, so R assigned 1, then while x minus I, and then in the loop body, I becomes I plus 1, R becomes R times I. What does that compute? Well, the name of the program already suggests that, right? But what is this arithmetic expression doing here as the condition of the while loop? That's another thing. So those of you who've worked with C know that C maps numeric values to Boolean. So anything that's non-zero is equivalent to true, and anything that's 0 is equivalent to false, right? So that's how C, in fact, you could even consider a definition of Boolean where false is equivalent to 0 and true is equivalent to 1 in terms of the definition of those Boolean constants. But other than that, anything non-zero would map to true. Okay, so that's the same thing here. So if x minus I is 0, then that's false when we're reaching the end of the loop. Otherwise, it's true and we continue the loop. Okay. So what happens here is we're just bypassing the parser, right? We're defining a statement directly. And then we define the store up here, and within the context of this store, we're executing S, right? And then whenever there's an assignment, for example, to R, it actually modifies the mutable storage cell, the L value associated with the variable R. So, any questions so far? Okay, so by contrast, in assignment 3B, so all of this, okay, this is actually discussed here. So in our language, we will allow previously unknown variables to be defined simply by assigning to them. So it gives it more of a JavaScript flavor, like a dynamic language. So that's the point I wanted to emphasize. So as opposed to the immutable maps in those two examples, MISC, Scala / imperative, as well as simple imperative algebraic, where the maps are immutable, which means whatever variables you're going to use in your program, I mean in your abstract syntax tree, would have to be created up front. Here, we don't want that. So here we want to be able to do this. We want to be able to say, all right, let's start up our little REPL, or mini.js, or as I said, mini.js is an overstatement. It's like a nano.js. So we want to be able to start with an empty memory, and then we want to be able to say, okay, let's create a variable x, initialize it to 3, and then memory has a mapping for that variable. Does that make sense? So those mappings from variable names to cells with some values stored in them. Okay, so that's the one key difference. And the easiest way to achieve this is to make your store a mutable map. And I actually recommend going that route. It'll keep things simple. If you use an immutable map, you have to kind of pass it around in more complicated ways, and then extend the map for evaluating the sub-statements of a statement and so on. So it's a little more complicated. So this is the recommended route. And then, of course, there's also a need to deal with possible failure, right? So because the program might be erroneous, and evaluation or execution of the program might fail. So how do you deal with that? Well, in a REPL, obviously, you don't want the REPL to crash if the user enters the wrong program. You want the REPL to say there is an error in your program. Try again, right? And the REPL should still be there. So that's why we have to deal with semantic values and failure. So, and we do that by defining some kind of value type, right? And that aspect is contained in the simple imperative example, the simple imperative algebraic example. So there is a, let's see, there is a trait value, and right now there's only one variant in this trait, because right now we're dealing only with numeric values. Okay, so numeric value is just something that represents an int. Why are we introducing the trait value? This is an example of future proofing, because in 3C we're introducing an additional kind of possible values. what kind of values, in addition to numbers, strings, booleans, etc., what kinds of values does JavaScript have that are more interesting values? Objects, yes. So you can distinguish between scalar values, like the little things, scalar, and objects, which are more like aggregate values, right? So that's right. So in 3C, we're adding objects to this, and of course, JavaScript objects are so widespread that they have developed a life of their own. They're called JSON, right? JavaScript object notation is just a very widely used data representation format, lightweight, lightweight alternative, partial alternative, right, to XML as an externalized text-based as opposed to binary data representation. So here we're just future-proofing this. We're going to have in 3C another variant of type value called instance or object or something like that. Okay, then another thing I wanted to point out is, let's see, let's take a quick look here. Back up for a second and go to AST, to our syntax. So here's a really interesting question. Here it says case class constant wraps around a value int, which it represents. Why do we need both constant and num? How are they different? Well, even though they seem to be very similar. Any thoughts on this? Once again, so abstract syntax and the executor or interpreter. So let me give you a hint. What do these things represent? What does the abstract syntax represent? Or where does a particular instance of an abstract syntax tree come from? Where do you start? So you start with a source program. What is that? A text file, right? If you take the text file, you feed it through the parser, then you get an instance of the abstract syntax tree. So in other words, the abstract syntax tree represents your source program as a data structure, right? So all of these things are part of what is called the syntactic domain. So these are just tied to your source. Whereas everything that's over here on the execute side, this is the runtime domain. So these are runtime values that can appear during execution. So it's usually helpful, conceptually helpful to separate those two things. To say, well, over here I have my syntactic domain, abstract syntax trees, and then over here I have my execution values, my runtime values. And what does the evaluator do? So it has a method basically this corresponds to the method. And really the main thing it does is it takes an abstract syntax tree and produces a result. So in other words, the evaluator or interpreter, just like we said earlier, so for arithmetic expressions, the evaluator took an abstract syntax tree representing an arithmetic expression. So that's the domain of the evaluator, the argument type. It produces a result type, so that's the codomain. It produces a result type of some kind of result value, which in the case of our expression evaluator was just int. So this was already detached from our syntactic domain where we represented integer values as a constant node with some int value associated with it, right? So we have these 3 nodes in the syntactic domain, but we produce just straight ints as result values. So here, it's the same thing, but because we are future-proofing this, we introduced another runtime value type or result value type value, and we created a variant called num to represent the case, that's the future-proofing, where it's just an int, right? But we have to have that little wrapper associated with our general result type value. And the future-proofing is that by doing it like this, as a trait with case classes that extend the trait, we can introduce more case classes that extend that trait. So in 3C, we're going to introduce an object type that also extends that trait. Okay, so that's that separation, right, between syntactic and semantic or runtime domain. Yeah, okay, so let's see. Yep, some of these things are going to be simpler in your project 3B. So in particular, this uses a technique called thunks, where a thunk is basically a function without arguments that you evaluate only when you actually need the result value. So at a later point. And this is required here because otherwise you're going to evaluate things too soon, and you're also going to evaluate things that shouldn't be evaluated necessarily. So like in a conditional, right, that's really the difference here, what makes an interpreter of a little imperative language with things like loops and conditionals more challenging and more complex than simple evaluator for arithmetic expressions. Let me illustrate it like this. So when you evaluate an arithmetic expression, like the ones we had in the earlier example, are there any portions of the expressions that you wouldn't evaluate? Or do you always evaluate everything in the entire expression? So if, let's say, you have an expression like this one, let's say, suppose, it's just, an arithmetic expression without variables. So 2 times 3 plus 7. Are there any reasons you wouldn't have to evaluate every little piece of the expression? You always have to evaluate the whole thing, right? Unconditionally, so you can evaluate it eagerly. All of the branches everywhere, you have to basically traverse the entire tree to get your final result. But what about in a language that has, for example, conditionals, where it says, if some condition, then evaluate this, else evaluate that. You have to evaluate only one and skip the other, depending on the condition. And the whole point of having conditionals is that you might want to skip something that, if you evaluated it under the current condition, it would crash or something, right? That's the point of a conditional. So that's what the thunking is for, so to kind of represent the potential evaluation of something, but not doing that evaluation until you actually decide, okay, the condition applies, so I have to go in and evaluate this branch. Okay, so that's what this is about. So It's just to represent a delayed evaluation on something. So you can have these potential evaluations and then perform them only when required. And I think, let me see, in this case, you probably don't, let me see. Yeah, you don't need it when you do it in the straightforward way. You need it only in the F algebraic way because those standard building blocks basically require you to represent all of these pieces of a syntax tree, of a result. As you're processing the syntax tree, it requires you to represent those uniformly. So you cannot ad hoc say, oh, I'm going to skip this or skip that, but the thunking basically allows you to have control over what really does get evaluated. So your 3B in that sense should be simpler and follow much more the MISC Scala example, where, for example, here in execute, right? So in execute, you basically use your host language or a construct in your host language to simulate the constructs in your little target language. You know, in this case, in our case, the mini.js. What do I mean by this? Well, okay, the while is a good example. So to represent the while in the simple imperative language, or to actually evaluate the while in the simple imperative language, we use a Scala while or a Java while. Okay, so the same thing would happen for the conditional. So when you have your conditional, it's just like this, you know, except, I mean, loops and branching are very similar. Evaluate the guard, and then if the guard represents true, then evaluate the then branch, else evaluate the else branch. So there's a conditional in your interpreter to deal with the conditional in your abstract syntax tree. Just like there's a while loop in your interpreter code to deal with the while or loop construct in your abstract syntax tree. That's how I would do it in 3B, to keep it simple. So basically, follow mostly this, but use a mutable map. Okay, so any other questions about the concepts and techniques of program interpretation that we need to make sense of Project 3B? Any questions? So today is the 3rd, right? So yeah, we have about a week and a half to finish this, so we should be good. Just don't over-engineer it. You know, that's why I'm saying keep the map mutable as opposed to having mutable cells. You don't need mutable cells then, yes.
Just one question. You mentioned earlier about how sometimes B can have an expression on the left side. Is that something you want us to include for this?
No.
Okay.
Good question, right. No, so that's why in earlier situations, I guided anyone who asked me to design your syntax in such a way that, like this. So this one's kind of like the way I guided you. So in assignment, just restrict it to having a variable name on the left. And that would simplify that part. Any other questions? Any comments, concerns? Okay. So yeah, I think this is going to be really fun because it'll kind of bring the abstract syntax trees to life, you know. So then the abstract syntax trees represent programs that actually do something. And that's really what this is about, right? So what we're doing is raising our own level of consciousness of what happens in program execution. So we have an intuitive understanding, but here we're actually implementing our own intuitive understanding as code. And so we're building a tool that's capable of executing a program or programs in this mini language. And that means, you know, we're basically able to build these kinds of general tools, because the difference between a mini language like this and a more full-fledged practical language is just that the practical language has a richer set of constructs and has, let's say, a more mature, more sophisticated tool chain, so that pays attention to performance consideration, because clearly when you interpret a program like this, you know, when you interpret programs represented as trees like this, execution can be very slow. So what you can do is you can try out the behavior of these kinds of interpreters. For example, if you evaluate the factorial or run the factorial example here in MISC Scala, you know, so you could kind of try the factorial with different arguments. You know, so what the factorial of which variable are we computing here? Well, it's actually clearly, you know, I and R are 0, you know, so it would have to be x factorial, right? How is that happening? Well, we're saying we're basically starting with I at 0. And then while x minus I is 0, which really means, so while x minus I is non-zero, so what this really means is, what we want is while I is less than x, right? So we had to figure out a way to write that, or something close enough, as an arithmetic as opposed to Boolean expression, because we don't have Boolean expressions here. So for this practical purpose here, x minus I is equivalent to saying x minus I not equals 0. Which means basically x not equals I, and if we start with I less than x, it's, for practical purposes, equivalent to say I less than x, right? So we're saying, okay, while I less than x, we're incrementing I, and then we're multiplying R by I. So it means we're multiplying right, and we are assigning 1 to R here, right? So there's a little inconsistency here, you know, for making the handling of all of the variables consistent, we could have said all of them are initially 0, and then we assign 5 to x and then 1 to R, and then we're just multiplying, so I goes up and up and up, so 1 times 2 times 3 and so on until we reach the desired value of which we're computing the factorial. Okay, so what you could do is just to observe that these things are fairly slow and inefficient. You could try this for increasingly larger argument values and see, kind of benchmark it a little bit. So in terms of Space consumption, that's also always a potential issue, but it should be okay for that because we're using a while loop here and not recursion. All right. So, okay, cool. Any other questions about 3B? So, I think I'm hoping we're all on the same page in terms of understanding the importance of getting started really early on these projects. So I hope by now everybody is carving out some time out of your busy schedule. I know everybody's busy. It's kind of a universal truth. So the challenge is just to kind of manage your time in such a way that you set aside some time at least to make progress on, let's say, a project like this one. Okay? But I'm here to help, in case you have questions. John is here to help as well. Any questions after today, just, talk to me as usual. So now I want to get started at least with a conversation about the techniques that we're looking at in Project 2B. So we'll want to look at section 4.3. And the one thing we noticed, in all of the examples that we have, so I'm going to pull up a few of these. Okay. All right, so this is the org chart example. So to compute the size of a node of an organization, well, if we have a base case, then we have some suitable result value for the base case, so in this case it's 1. If we have the recursive case, which means we have children, 0 or more, but it makes sense really mostly when there could be more than one child, right? Otherwise, it's not really a tree. And what do we do then? And let's look at expressions also. Let's look at this side by side. Right. Okay. All right. So, and then also in your shapes, right? So let's pull up shapes. Same thing. Right. So as you remember, so for the Android shapes example or project, for group, what did we do? We had to say for each child of this group, compute the bounding box of that child, right? And then somehow, based on the bounding boxes for the children, figure out the value of the bounding box for the group, generally speaking. Does that make sense? That's what you did in this example, and you redid it in our shapes project, right? Then, if we look at org chart, very similar. So here we're looking at the size behavior as opposed to bounding box behavior. So here we basically do the same thing. So we say, well, let's look at the sizes of each of the children. That's what map does. Map is implicitly a loop, although it doesn't have to be implemented as a loop, right? When you recognize the fact that the step of applying the function f, which is the argument to map, to each item in the collection, those are all independent invocations of that function. So they could be executed concurrently without any harm done, right? They could safely be executed concurrently, but that's kind of a digression. That's something we're going to look at toward the end of the semester. But the idea is it's kind of it's similar, or let me say it like this. Using a loop instead of the map is just a more specific way of achieving the same result. Meaning, you have the children and you want the sizes of the children. Right? Loop is one way of achieving that. Map is a more general way of achieving that, where you don't really care in which order it happens, although in a non-parallel implementation, under the hood of map would still be a loop. Okay? But you have the children, you get the sizes of the children, and then you combine those results that you got for each child into a result for yourself. Right? So what I'm trying to emphasize is that that's the same pattern, the same kind of recursion pattern, right? In an imperative approach, it would be it would look more like a for loop, right? So for each shape in the group, get the size of that shape and add it to the sum. And here we're just doing the same thing, but using functional techniques like map and then the sum method to add up all the items in the collection resulting from map, which are the sizes of the children. Okay. Well, what would height look like? Well, here it's got the 3 question marks, meaning not yet implemented. Right? So this is a type-correct way of saying not implemented, and when you actually get there, when you try to evaluate this, it will raise a not yet implemented exception. Okay. Well, how would you implement this? Well, same way, right? Children.map, height, and then at the end, max, right? But what I'm trying to say is, okay, so I'm going to write it down just so we can look at it side by side with the size method. So children.map, height.max. Okay, so which part is in common? This part, right, the map. The map is in common, right? And then the fact that we're combining the results that we get for each child. Okay. Let's look at some other examples. Expressions. This seems to be different superficially. Is it different? And why is it actually different? What's the difference between the org chart structurally and these expressions? How many children can a node in an org chart have? It could have one, but could it have fewer or more than one also? It could have many, right? So 0 or more, right, in our org chart example. But what about here in our arithmetic expressions example, the way this example works? I mean, the way our kind of simple expression syntax works. 2, right? Exactly 2. But in shapes, we also had 0 or more, like in org chart. Okay? That's why I brought in shapes also. Anyway, if you... Let me just make that one point. You could have written the plus, for example. You could have written it like this. To make it look just like that. Right? You could have written list L R map evaluate and then full left 0 and then plus, right? And now you see again you have the map and then you have some fold as a way to combine the values, right? Like this is a fold because it applies max successively to the items in the collection that you're looking at. Or it's a reduce really because this wouldn't work if there's only if there aren't any children, then the max wouldn't work. Okay. So the point I'm trying to get to is that when you have tree structures and you want to express your typical recursive behaviors where you're traversing the tree and computing some kind of cumulative result for the tree, that it seems like every time we're doing it in the same basic way, meaning we're recursively applying the behavior we're implementing to each child when we look at something like a group node or any kind of composite node. So we're recursively applying the behavior to each child, and then we're doing a kind of a reduce step. And that's not a coincidence. So this is a map and this is a reduce. A reduce is just a fold, basically. So we're doing these two steps to implement behaviors on the composite tree nodes. And that's always the same. And what's different every time is, well, just the behavior and really what we're doing here. So the key difference is, because this is just the recursive invocation. So recursion, and same thing here. I mean here, this guy, the argument. And really the main difference is what we're doing here at the end and what we're doing here at the end or anywhere else at the end, right? Like in org chart. That is the only difference, really. But there's always this map, the behavior itself applied recursively to my children, and then do something with those results. And the only difference is what you're doing there. So in some sense, this is what you're seeing here is equivalent to this idea where fold on lists can capture most of the kinds of behaviors you want on lists, like adding up the items or finding the max of the items or those kinds of things. So what you're seeing here is a step toward discovering a tree equivalent of the fold that we already have for lists. And actually where this leads us is we can actually have that kind of thing, something equivalent to a fold, but for trees, for these tree-like structures. But we can actually take this even further, which is we can consider trees, lists, and all of these things as basically equivalent, parameterized by some kind of structural piece, right, that changes. But we can write the code for the fold-like operation only once, and it could apply to all of these seemingly different structures because they can be unified by looking at them in a certain way. So that's really what Project 2B is about. It's like it's basically like using a library that provides these general building blocks and redoing 2A in such a way that it uses that library, which would mean you don't have to write the part that performs that applies the behavior recursively to the children. It'll do that for you. You just have to parameterize it with how you want those results to be combined. But we'll continue here on Thursday. We're out of time now. But I think, it's going to be, it's definitely challenging just to kind of wrap one's head around this and the generality we can get. But, once we do that, I think you'll find it quite interesting and actually useful because in a practical sense, it does eliminate the amount of different code you have to have for these different data structures, right? So from a software engineering point of view, the more code reuse you can achieve, as long as you're not introducing performance problems, right? Because there is that tension possibly, but the more code reuse you can achieve, the better off you are. Okay? So see you either at the office or on Thursday.